operations on one or more binary inputs and produce a single binary output. So the ones that are taught are basically the buffer, which is the first one. I don't know why it's called yes, but it's a buffer. So it will have inputs of, it won't change the input. It will be the same thing as the output. But then it will be useful for the parts of memory later on. And for the NOT, it just switches 0 to 1 and 1 to 0. And it's a gate that only outputs 1 if both A and B are 1, or is if any of the A or B are 1, it'll output 1. XOR is if there's an odd number of 1s, it will output as 1. So if this was like a 3 XOR gate, then it'll be the same thing. It has to be odd number of 1s. And NAND is just an AND gate, but with a NOT after that. And a NOR, it's the same thing as an OR gate, but you put a NOT gate after. And XOR, XNOR, it's just the same thing as an XOR or an exclusive OR, but you just put a NOT afterwards. So that's just the logic gates, and I think you should already be familiar with these logic gates. So the first thing I would like to go over is how to find Boolean expressions from a table. So there are two ways you can do it. You can either do sum of minterms. So you find the minterms, which are basically the rows on the rows of the table, which result with an output of 1. And then afterwards, you just sum the minterms. So you use plus operation. Or a product of max terms, and max terms are just, you find the rows in the table where the output is 0. And then you use the AND operation, or you multiply basically. And then after you find the Boolean expressions, you can convert them into the logical circuit by just seeing the expression and just following it using AND and OR gates. So for example, if we have a table like this, then we want to find the minterms, then you just find the rows that have a 1 as the output. So this is the first row, second row, third row, fourth row, 9th row, 11th row, and like the last 2 rows. So if you want to get the minterms, you just write each row. So let's do one by one. So the first one is A has 0, B is 0, C is 0, and D is 0. So that means that the first minterm will be A naught, B naught, C naught, D naught. And the second one is when A is 0, B is 0, C is 0, and D is 1. That's A, B, C are not, and D is just D. And if you repeat it for all the ones, so the next one is going to be A naught, B naught, C, and D naught, which is this one. And you can repeat it again for the fourth one, A naught, B naught, C, and D. And if you repeat for all, and then you take the sum, so sum is like you take the OR of all these minterms, then you'll get the expression for Y. Like it'll be the Boolean expression. The second option you can do is generally if there's more rows that have 0, if more rows result in 0, you use the product of max terms because it will make it simple, like it'll be shorter, the expression. So you just focus on the rows with zeros. And now you treat, if it's a 0, it's going to be A. And if it's a 1, it'll be not B. So it's kind of like the opposite. So you focus on the rows with 0. So in this case, since it's a 0, it'll be A plus, since it's a 1, it'll be not B plus, if it's a 0, it's C plus D. So that'll be the first max term. Then you repeat it for all the rows with 0 as the output. So you can see that for another example, like this, the next row of 0 will be A, B naught, C, and D naught. So it'll be plus. So that's how you do for the minterms and max terms. And I think this part is still quite simple. So now if you want to make the most simplified one, because right now, if we just use the product of max terms or sum of minterms, it's very long. So we can simplify these expressions by using K-maps or Carnot maps. So the rules for K-maps is, first of all, you just need to make it into like a K-map, like this table, where you convert the table of columns, table of rows into a table like this, the K-map table. And then afterwards, there are a few things that you need to consider when you're trying to do the groupings, that the boxes must cover all ones and non-zeros, because I'm doing the sum of minterms one. Then boxes must be rectangular, size of each box is power of 2. It's either 2, 4, 6. So 2, 4, 8, 16. So don't do 3 or 5. And boxes may overlap. And the ones that I want to emphasize on that I think that people tend to forget is that boxes may wrap across edges of maps. So like it can wrap around the edges of the table. And sometimes in some occasions there are don't care values. And you just treat them as 1 or 0, whatever helps simplify the table. So in this case, there is no don't care, but you want to see the grouping. So the first grouping, that's pretty obvious, this one. And then we want to group the next two in the bottom, like the 3 left, the 4 remaining in the bottom half. So if you just did these two together, it would be not efficient. So we also choose the top. So we wrap it around the corners. So we this, and this. And the last two we just group together because we can't do a group of 4 here, or there's no more ones nearby it. So just be careful that we can wrap around the corners because students tend to forget this and it may lead to your answer not being the most efficient. Then after you have already done the groupings, you can make it to the expression by just writing it. So for example, the first grouping, this one, we see that what's common is that in these two cases, it doesn't matter if D is D naught or D, it will still lead to a 1. So we omit the D. And in this case, and in this case, these two cases, we don't care about the C because it shows that with C and without C, it will be still the same. So after you just do groupings, just see which one are the same, and then it'll simplify to the expressions A naught, B naught, and B naught, D naught, and ABC. So to remember, we still plus the different groupings. So that's how you do some the K-maps. So the next topic that I'll go to is about circuit devices. So circuit devices, there are two types of circuits. One is combinatorial. So a combinatorial circuit is a type of logic circuit where the output depends only on the current inputs. So remember that this is different from a sequential because sequential circuit depends on both the input as well as like the history or basically the past date. So this one has two things that you have to focus on, the state that we're in and as well as the input. But if this combinatorial is just the input. And a few of the circuit devices that are mentioned in your lecture is the first one is a multiplexer. So a multiplexer takes in many inputs and you choose a selector, which is like, basically this one is like chooses which of the inputs you want to put out. So if this one is 0, it generally goes to A. If the selector is 1, it'll go to B. And if you want to have more inputs, you just have to make sure that you have enough bits to choose for the selector. And then a decoder is a little bit different. So you have no selector basically, but it has an inputs. And basically the n inputs for, it's like you think of it as like some code. So if it has some code, it will output one of the lines. So if you have some certain input, it will output one of the another line basically. So it's basically like you give in some input and it'll give it some output. And remember that if you have n inputs, you'll have 2 power of n outputs because each of them can be it's like a binary, so it's 2 power of n. And then we have adders. So there's two types of adders. There's a half adder. So the half adder has 2 bits as input and 2 bits as outputs. And this one's like the very simple one where it's like, which can't really be used too much. So generally there's a more important one, which is the full adder. Oh, this one's, and the full adder takes in 3 bits and will output 2 bits. There'll be 2 outputs, not bits, like 2 outputs. And yeah, so the difference is just this one has a carry in that it can take, while the half adder cannot do a carry in. And the reason we need a carry in is for the addition later and also for the subtraction. And a ripple carry binary adder is just you put a lot of full adders and you connect them one after the other, and then you can add 2 numbers, 2 binary numbers. And if you want to have a subtractor, it's almost the same thing as a ripple carry adder, but instead you also have an option to do subtraction. And to do subtraction, we do the two's complement. So if we want to do like A minus B, then basically, if we're given the inputs of B and A, we make sure that B turns into the two's complement. So if you want to do the two's complement, you invert the bits. And then you add 1. And add 1. So you do these two things. And then afterwards, you basically add it. So if you want to see the circuit on the right circuit allows us to do both addition and subtraction, because if M is 1, so if we give a signal of 1, then the XOR gate for each bit of B will result in the B to be inverted, because if in an XOR, if we already have a 1, then the other one, like the input will just result in it'll be inverted. But then if it's a 0, then the B bits will remain the same. So it'll basically be addition. And after it inverts it in the XOR gate, we also have a CIN. So the CIN will just basically add another 1, which is the add 1 here. So that's how the subtractor works. Then something short, which is about converting decimal to binary and vice versa. So if you want to do decimal to binary, then the main way you can do is just use division of 2. So you divide 125 by 2, we get 62, and get the remainder, you put on the right side, and keep doing this until you get 1. So once you get 1, you just read the number you get in this way. So the number will be 1, 1, 1, 1, 1, 0, 1. So just remember to read it from the bottom to the top. Or another way you can think of it as like 125. The biggest number is the biggest power of 2 is 2 power of 6, right? Like 64. So it'll be 2 power of that's 6. So it'll be because we have here. So here's 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6. So we're gonna have a 1 in the 2 power 6 one here. A 1, and then afterwards by plus 32, the second biggest one, it's still gonna be below 125 because it's 96. 64 plus 32. So we put another 1 here. And afterwards, if I get 96, and I add 16 again, so it's still going to be below 125. So we put another 1 here. So this will give you 100 and, well, then if I add 8, it still will be 120. So that means that we still can put it, we put a 1 here, and if we put a 4, we add a 4, it'll be 124, so we still can add a 1 here. But if we add a 2, it'll be over 125, so we have to put a 0 here, and then we just add a 1 to make it 125, so this will give you the same thing. So either method works. Yeah, so it's just whatever you feel like you're more comfortable with. But if you want to convert the binary to decimal, you just need to know that each of the digits in the binary number has a certain value. So the first one is 2 power of 0, and 2 power of 1, 2 power of 2, 2 power of 3, 2 power of 4, 2 power of 5, 2 power of 6, 2 power of 7, and you just multiply it. So if it's a 1, just multiply it by 2 power of 0, you get 1. In this case, we have a 1, so we multiply by 2. But in this case, we have 0, so we multiply 0 and 4. And if you keep repeating for all the digits, and then afterwards you add them up, you'll get the decimal value. Then the more like the harder topic that people probably forget is about latches and flip-flops. So in this topic, you're most likely going to be asked to like fill up a waveform diagram. So a waveform diagram just tells you how, if you put in inputs, how some outputs might change, or some part of the circuit. Like what's the value at a certain part of the circuit, whether it's high or low. And one thing to remember when you're drawing these waveform diagrams is that there's always a delay between the clock and the output. So if we have something like here, and then we want it to change, we have to make sure that it happens slightly after, like that. So there's some like propagation delay. So just remember this because I think it's pretty important because people probably forget. So don't make it a line. Just make sure that you have like a small delay afterwards. Yes, so that's just a waveform diagram. There'll be some questions later after I finish the latches and flip-flops part. So the first latch we're going to be talking about is an SR latch. So an SR latch, you think of the words like S and R as set and reset. So if both of them are 0, then it doesn't do anything. So it'll just keep the previous value. So in this case, if the previous value was 0 and 1, like in the Q and QT, like the Q naught, then afterwards it'll still be 0 and 1, and same case for 1 and 0 and 1 and 0. So just remember that if your S and R latch is at 0, 0, then it does nothing. Then if R is 1, just think of it as you have activated the reset. So we want the Q to be 0 because we're resetting it. And then I guess the other one just follows. So just focus on generally just one of them, like the Q, and the Q naught just follows, like it'll be the opposite. Then if S is 1, then it sets it, so we set it to 1. So you can see that no matter what value we put, no matter what the state was before, if we have 1, then the Q will be set to 1, and the opposite for Q naught. Then if it's S is 1 and R is 1, this is kind of like the forbidden state because it will result in both Q and Q naught to be 0 and 0, which doesn't really make sense because they should be the opposite of each other. So this is why we're going to make some other types of latches in the next few slides. So another type of latch is the SR, the not S, not R latch. And it's almost the same thing, but like the inverse of it, like the opposite. So instead of, you just think of high as when thing is 0. So if it's both are 0, 0, then it's the forbidden state again. And if we have S not as 0, then it will set. Then if R is 0, then it will reset. And if they're 1s, it's basically just think of it as low. So it just stores. So it's almost the same thing as the SR latch, just kind of like the opposite. Then if we want to make a clock SR latch, it's basically just you put another NAND gate here, and you put a clock. You attach a clock to the NAND gates, and this clock basically helps you do something where if the clock is at 0, then you just store, so you don't change any values of the QN and QN naught. But if it's 1, it basically just acts as an SR latch. So you have to read the inputs, and then it might change the QN. But then the clock SR latch still has the problem of if my clock is 1, that I can put in S and R as both 1, which is not good because this is like the forbidden state for SR. So we want to remove this forbidden state by making a D latch. So if we have a D latch, a clock D latch, then we only have one input, and having a NOT gate going to the other input where the R was basically just inverts it so that what goes to S and what goes to R won't be the same. It'll be the opposite of each other, which is good. So now we can store if we make E go to 0, and we can change the value by putting a D, basically. Putting some value into D. So either we put 1 or 0, and it will set or reset. So that's the purpose of a D latch. It's just to make sure that the forbidden state doesn't happen. Then afterwards, let's go to flip-flops. So flip-flops are basically just you have two latches that you attach to each other. And basically what it does is it makes the value of Q only change at either the rising edge or the falling edge of the clock. So when you're doing the waveform diagrams, you just have to focus on the parts when the clock either rises if it's a positive edge, and when it's a negative edge, you just make sure when you focus when it's falling. So yeah, just flip-flops are just almost the same thing as latches, but they're edged. So they only change at the edges. So there are four types of flip-flops, and it generally helps you to, like, when you see the circuit, then you want to identify which one it is, because then um, you can easily draw the waveform diagram. So the D flip-flop is the simple one, where you basically use D latches, and it only has one input. So it's just based on whatever if it's one, then it'll basically just act as like the setting part. It'll set Q on the edge, and if it's zero, it will reset. And SR is basically the same thing as so an SR flip-flop is basically like an SR latch. So based on what the combination of S and R you give, then at the certain edge, it will, like, either the positive edge or the negative edge, it will change according to what the input of S and R is. And a toggle flip-flop or T flip-flop just switches between a 0 and 1. So if your Q was at 1, then at the certain edge, it will go to 0, and vice versa. And a JK flip-flop is basically just a combination of an S and R and a toggle. So you have more options basically. So that's the kind of flip-flops. Then I'll be going over some past paper questions that were given to you guys about these topics. So the first question gives you some circuit and you need to complete the waveform diagram. So I'll give you guys like 2 minutes to try and do this question, or think about like what you guys will do if you encounter a question like this. Okay, so I'll go over this question. So the first thing we need to find is Q0. So Q0 will be the one here. So what you should just try to figure out is that this one is a latch, and we need to just focus on when the clock is um, when the clock is up, then we focus on the output because if it's at 0, then it won't change anything. So just focus when the clock is up. So in the start, because the clock is not up yet, it'll just be 0. But as soon as the clock goes up, then we need to focus on the combination of S and R. So the combination of S and R, then because S is 1 and R is 0, then that means that we need to flip it up. So because it's SR lab, so S is 1, R is 0, it means that we go up, then we go up. And now you see that S changes, but then both are 0, and in SR flip-flop, sorry, in SR latch, if both are 0, then we just store, so we don't do anything still. But as soon as the R goes up, we need to go down because we need to reset. And then just keep going. And then here, R goes down again, so both are 0, so it doesn't matter anymore. So we still keep going. And then at this point, S goes up, so we set again, so we need to go up. And then the clock falls down, so we don't need to, like, we don't have to worry about what happens to S and R in this interval. And when the clock goes back up, oh, there's a question about propagation delay. I think you should, yeah, you should. Yeah, so in the first one I kind of forgot things. Um, so yeah, so you should show propagation delay. So the first one, just make sure you put a little gap. In the second one, I already put a gap here. So you just need to put a small gap. And here, we see that it goes back to reset because R is 1. So there's a small propagation delay here. And then afterwards, R goes back to 0. So S and R are both 0. So it still stays at 0. But when S goes back to 1, then we should go up. And when S goes back to 0, it doesn't change. So we go back down. And only when R goes back up, we should, no, because S goes back down, it doesn't matter because both are 0, so it doesn't reset. But when R goes up, then we need to reset it. So go back. And then afterwards, there's no more changes, so we just stop, and the clock is gonna be. Then afterwards, the clock is 0, so there's no more changes. So then we just need to continue. So that's how you do it for this one. Then for the other one, the Q, since there's two latches, you can think of it as a flip-flop, but there's a modification because there's two NOT gates here. So basically what we'll have here is the actual, so if you think of this as a normal SR latch, then this will be like a Q NOT, and this will be Q because of those NOT gates. This is one way you can think of this question, which will be much faster. Or the slower way you can do is just treat this as another latch and just see the inputs of these two inputs. And then just do the same thing what we did for Q0, but with the new inputs of Q0 and Q0. So that's the second way you can do it. But the faster way, which we think of this as a flip-flop, you just first have to identify that this is a negative edge flip-flop. So because it's negative edge, that means that we only need to focus the when the clock falls. So there's two intervals I need to focus on, this one and this one. And initially Q is, so you think of Q as Q naught. So because initially Q is 0. Q naught will be basically 1. So we start as high. And then when it hits this clock, then we can see the values of S and R. And depending on this, we will adjust our Q. So since S and R is S is 1 and R is 0. So that means that we should set. So initially, if we had Q here, it would set to 1. But because we have Q naught, it'll be the opposite of Q. So it'll go down. And then you just continue the line until the next boundary where we have to consider. And in this case, we have S as 0 and R as 1. That means that if I had the Q at the end of the flip-flop, I would have to set Q to 1. But because we have it inversed, so then Q naught is going to be 0. Sorry. We would have to set it to 0 because we reset. But because we have Q naught, we have to set it back to 1. It's the opposite. So yeah, that's great. I should draw it. Oh yeah, so it should be more right a little bit. So it's something like that. So that's how you do this question. If the question about if clock is high and it's in forbidden state, I guess I don't think they'll ask a question like this because it doesn't really make sense. But if it does, like if it's asked, then just follow the table because the table says that it should be like both 0, I think, or both. Yeah, I think it's both 0 or both 1. I forgot. But just follow the table. But generally, they don't ask that. Like, you can see in this question that there is no case where when the clock is up and both S and R are the same, like they're both high. And how do we know if it's a latch and which is a flip-flop? So if you kind of need to know the symbol for latch, something like this. And if we have two latches connected together, then it becomes a flip-flop. But then they can also mention it in the questions. So just like see that if it's a latch that are connected to another latch, the second one is basically the whole thing is a flip-flop, like the output is a flip-flop here, but if you want to like the output of the first one, it's gonna be a latch. Because remember that two latches make a flip-flop. So just remember the symbols and then you can do that. Yeah, so just remember that these are latches, and if you combine them together, it becomes left flip-flop. So that's how you do question 1. Then I'll go over to the next question. So the next question is just some short questions. So the first question is if R naught is high and we are in a not S latch will be set to 1 when S naught is. So remember that if R naught is high, then basically it's low. Like you treat it as it's low. That means that S has to be low because we want to set. So in a not S, not R latch, we want the S to be low to set it. So the next question is how many gates do we need to build an edge triggered RS flip-flop? So just remember that in a flip-flop, it consists of two latches, and in each latch, we need 4 gates, so in total it'll be 8. And each latch, 4 each. So in total it'll be 8. Then the question 3 says consider the Boolean expression. So we want to see which one of these simplified this. So if we want to see that, we just need to simplify this expression. So we can use the distribution. So we get A naught plus D naught C, sorry, the B. A naught B plus A naught C plus AC. So if we can factorize this, we get A naught E plus C A naught plus A. And we know that A naught plus A is basically like A or not A. So it's going to be 1. So it's just A not B plus C. So this will be the third one. And then in a one-hot decoder, if we have 32 outputs, how many inputs? Remember that if we have n inputs, we have 2n outputs. So then if we have 2n outputs, then we just take the log 2 of this. So this one equals 32. So then if we want to solve for n, we just take the log, so log base 2. So the n equals log base 2 of 32. And that equals 5. So that equals 5. So let's try to solve this question. Then let's move on to the next question. So the next question is about converting binary and decimal. So the first question is convert 35 in decimal to binary. So if you want to convert that, there's two methods, the division method or the one that you find the powers of 2. So let's just use the division method. So we get 35, and we divide by 2, we get 17, remainder 1, and we divide by 2, we get 8, remainder 1, then we divide by 2, we get 4, remainder 0, and divide by 2, we get 2, remainder 0, and then we divide by 2 again. So if we divide by 2 again, then later we get 1, remainder 0. So then if we want to read what number is, it'll be for 1, 0, 0, 0, 1, 1. And generally, in most questions, I don't think this question specified, but there'll be a certain length of the number that it should be. So like in this case, they didn't specify, but you can just do like 8 if they don't specify. Just pick a reasonable number. But they probably will specify how much bits to do it, and you just put extra zeros if you need to. So in both the signed and unsigned, it'll be the same thing because it's a positive number. But in the second case, because we want to find a negative number, then there's no negative number for unsigned, so we only need to find for the signed version. So the signed of minus 35. So basically in binary, if you want to convert to a minus, we invert the digits and we plus 1, we find the 2's complement. So if we want to invert the digits, so we get 1, invert, we get 1, 1, 0, 1, 1, 1, 0, 0. And then after if we add 1, so then plus 1, so we get 1, 1, 0, 1, 1, 1, 0, 1. And this will be your number. Just remember that this one represents 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3, 2 power of 4, 2 power of 5, 2 power of 6, and this will be like the negative one, negative 2. So then the next part B tells us to calculate the value of 35B minus 51. So again, it says to do it in both using binary subtraction. So you cannot just, like if you want to get full mark on the type of question like this, you can't just subtract them and get minus 16 and then convert it to this binary, but you have to find a 2's complement of 51 and then subtract them. So 35 was the one before above here. Then 51 we can find 2, so we get 25, remainder 1. And then we get 12, remainder 1. Then we get 6, remainder 1, sorry, remainder 0. And 3, remainder 0. And then divide by 2 will be 1, remainder 1. So our number for 51 in binary is going to be 1, 1, 0, 0, 1, 1. And then if we want to get a 2's complement of this, we just first just make sure that it's in 8 bits also. So you make it into 8 bits, we add another 2 zeros. No, in 8 bits. And if you want to 8 bits, and then your number won't have enough to do negative. So now we want to invert it. So we do 1, 1, 0, 0, 1, 1, 0, 0, and we add 1. We get 1, 0, 1, 1, 0, 0, 1, 1. Then it's the 2's complement, so it's basically the value of minus 51 in binary. And now we just need to add the 2 numbers. So if we add the 2 numbers, 1, 1, 0. It'll be 35, which is 0, 0, 1, 0, 0, 0, 1, 1, plus 1, 1, 0, 0, 1, 1, 0, 1. That'll be 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1. This is what you get. And that'll be your final answer. So then let's move on to the next question.
Sorry, there's a question. Someone asked, why are we having it in 8 bits? Like, why do we decide the result to be in 8 bits?
Oh, because if we want to store like a larger number, like 51, you need to have more bits. You cannot have it as just this amount of bits. Like if you have it just as 6 bits, you cannot store until minus 51. So you just need to make sure that you have enough bits that the range of numbers you can store is like within the value. I think you can also do it with 7 bits, but you cannot do it anything less because later your value of your assigned number won't be enough to store the 51, like minus 51. So that's like you need to make sure you at least have a number, like enough bits to store this. Or if the question specifies, then you just make sure that you align it with the question.
Okay, thank you.
Okay, so let's go to the next question, question 4. So as we don't have not much time, I'll just go over this question. So for this question, again, there's another latch, like 2 latches and another 2 latches. And you can see that A is the input and B is like the clock. And we first need to find the T1, T2, and we will find X and Y. But then if you want to try to find X and Y first, it's very hard. So generally first find the ones that are closer, which is T1 and T2. And you should notice that they're going to be the same thing because I put A in both and they're the same latch and the clock is both having the same value. So if you know T1 and T2, just focus when it goes up, and when it goes up, you just see the value of A. So when B goes up, so B is the clock. So when the clock goes up, see the value of A. So since the clock is up, but now we have to read the value of A. So we go up, and since it's B flip-flop, we just follow the A. And now it goes down, and then keep following A, and then the clock stops, so you just hold on to the value, and when the clock goes back up, then you follow the value of A. So when the clock is up, we follow the value of A, so it's still 0, change it, But when it goes to 1, you need to go up. And then you go down. And then afterwards, just hold it. And then when the clock goes back up, you should see A. And then it goes back down. And then the clock, you just follow the A. Then after clock stops, you just keep going. And since T1 and T2 are the same, then you would just draw the same thing for T2. And then for X and Y, those two are a little bit harder. So the easier one will be Y. So Y, um, you can think of this as, so you see that the clock of B goes to this latch. So that means this one is a D flip-flop. This is a regular D flip-flop, but it's negative edge. So just remember the circuits for positive and negative edge. Because now once we have identified it's a negative edge, then we only need to focus when the clock goes down. So there's 3 spots you have to focus. So now we focus on only on these values and we see the value of A. So initially Y is 0, and at this value of when it goes down, we just need to see that the Q is, sorry, the A is 0. So we still go down and go to the next time when it goes down, which is here. And you can see that A is still down, so you don't do anything. And the last time when it goes down, A is still down, so it just, yeah, so this is the fast way where you can just think of it as a flip-flop. The slower way will be just treat this as an input, T2 as an input, and just treat this as a latch. And you can do the same thing for T1 and T2, like how we did that, but instead with T2 as the input. And the last thing is just for X. So for X, the difference is between X and Y is that X, the clock is from T2. So now what I do is just treat this as a latch by itself, but with the clock as T2. So instead of reading from B, you just read T2, but the input is still, the input is T1. So you read this as the A, so this is your new A, and T2 is the new B. Then just do the same thing basically. So when the clock is down, things should be down. Then when the clock goes up, we read A, so A up, so that means that we should go up. And then we just follow it. If you keep following it, you'll get a graph like this. So it's almost the same thing, just that there's a propagation delay. So there should be a delay between anytime it goes down and anytime it goes up. So that's it for this question. And then, sorry, questions. So how do we identify if it's a regular flip-flop or those with edge? So all flip-flops have edges. So are you like saying if it's positive or negative edge? So if it's, you just need to see where the knot sign is. So it's because the knot is in the second one, it'll be a negative edge. But if it's in the front one, and the second one does not have it, it'll be positive edge. So just like make sure that you see where the knot of the clock is, like the knot coming from the clock is basically the position of the knot gate. If you're confused between like latch and flip-flop, it's just if these are latches and I have two connected to each other with the same clock, then it will be like the output of one connecting to the other one. Then the overall circuit of this part is the flip-flop, but individually there are latches. It's like in your lab. So how did you make your flip-flop? You use two different latches. I use two latches and you connect them together. So like you can just treat each thing as like a latch. And T2 is low. Why do we still need to change x to low? I don't think you changed when T2 is low, we didn't change it to low. Is it like this if it's this, it's just propagation delay. Because you can see when the thing is low, our value of x does not change anything. This gap is just propagation delay because it's supposed to change when A is here, but we just we didn't we don't do it immediately, so we have the propagation delay. Like just treat like this part is the same thing as doing the very beginning where you do A and B together. Like you see that clock basically moves at the same time, and you just do both at the same time. Like you just treat them both as inputs and just basically just repeating what we did above here, but for we need two different values now. So T1 is the A and T2 is the B. Yeah, I guess like it's hard to determine which one is first though, like because they're both at the same time. So I guess I know what you mean, like because the clock and the things set are the same time, but it's like you don't know if this one goes down first or this one goes down first. So I think it's okay just to just go down like normal. Like in this case, we go both of them go up, we make it go up because even though they happen at the same time, something like that. So that's it for this question. Then the last question I have is some short answer again, because I think like a lot of the past papers had this, but I don't know if you guys will have it. So we can go through it quickly because there's not much time. So the first one, if you want to check if they're equal or not, you just need to, one way you can do is just add a double negation and then use the Morgan's law, and you can realize that they are not the same. But the second thing you can realize is that this is an OR gate and this is a NAND gate. And the second one is you can just use like distributive law, something like one of the examples before I did, and you realize that they're the same. Then the next one is you can implement every gate using only AND gates, and this is false because there is a gate like NOT. You cannot do with only AND gates. And you just need to find one gate that you cannot do it, and this will be false. And a ripple carry adder is an example of which circuit is combinatorial because we only need to care about the inputs that will result in the output. And the last question is if S is low, an RS latch will be set to 0 when R is, and it should be high because we want to set in an RS. If R is 1 and S is low, then we'll have it as reset. So that is for this question. And before we move on to the next question, do you guys want to have a break? And if you want to have a break, do you guys prefer having like a 10-minute break now or a 5-minute break now and another 5-minute break after at 4 o'clock? You just like write in the chat if you guys want to know.
Okay, let's just do it like this. I'll have a boost algorithm like practice, like shortly after this. So let's go until that part first, and then we'll give a 5-minute break at the same time, so you guys can solve it while you guys have break. What does that sound? Yep, I think that's it. Okay, we're continuing. Just for a bit, like just 2 slides over. And let me share my screen. Sorry, Valdy, can you unshare so I can share mine? Thank you. You guys see it? right, can you guys see the screen?
Yeah, we can.
Okay, cool. All right, so now we're going to the next part of the course. So this one will talk about the microprocessors stuff. We start with Booth's algorithm, then we go to data path and control unit. We'll talk about memories, the three types of instructions, and the data path flow. Okay, so let's start. So multiplication is a very important operations. But it can be quite complex, right? If you think about it in like computer perspective. Let me know if my audio is slow or bad quality, okay? So there are like three ways to do multiplications. So first of all, we can make we can build a circuit made up of layers of adders. Hang on. Let me see. Okay. Um, can I have a pointer? This one, right? Yep. Okay. Yeah, so we can have like layers of adders which are staggered. This kind of like mimics how we usually do multiplication, where we add like each row. However, the problem about this is we are using too many gates and uh, wires. So in terms of like the clock complexity, it's really efficient. It's O of 1. However, in terms of size and number of gates, it's O of n squared. So we want to make something better, right? The second method is similar to the first one, but instead of like adding everything, we have an accumulator which uh, adds it like step by step. So you add one, then you store that value, then you add another one, and you store that value. So this one is O of n in both clock and size complexity. However, there's another method that is even more effective than the second one, which is called the Booth's algorithm. So here it is. Right. So Booth's algorithm. It's quite simple once you get a hang of it, but why do layers of adders have a cost of O of 1 clock? Okay, sure. Yeah, because you just need one clock cycle for this. Like once you put the input in one clock cycle, you'll get like the whole output out. However, for say for the adder and accumulator one, uh, this process needs to loop n times, which is like the number of digits of which you're multiplying. So that's why it's O of n in terms of clock. Does that make sense? Okay, nice. Right. So Booth's algorithm. So it's quite simple, but it tends to come out in exams. So let's cover it. So the steps are, first of all, if you want to find A multiplied by B, first you have to decide like which one is which. Then you add 0 to the rightmost of A. And then for each bit of A, you need to repeat these 4 steps. So first of all, you check the last 2 bits. If it's 0, 0 or 1, 1, basically if it's the same, you do nothing. If it's 0, 1, then you add B to the highest bit of the result. If it's 1, 0, you subtract B from the highest bit of the result. And then finally, whichever A, B, C case you get, you need to arithmetic right shift both A and the result. Arithmetic right shift means you shift to the right and then you follow the sign bit. Don't forget this. So we'll have like a practice question. Let's try do a 3 times 5. I'll give you 5 minutes together with your break to solve this. It's quite easy. One tip from me is, first of all, when you get like multiplication of 2 base 10 numbers, you want to write them down in binary first. And then I find it also helpful to write the negative value of like one of the multiplicand as binary too. So in that case, it's easier for you when doing the subtraction. So you just like add the negative number. All right, so let's meet back again in 3:15 after a break to discuss this result. See you guys in 5 minutes. Oops. All right, it's about 5 minutes. So let's try to take this up together. Yep. Okay, so I hope you guys can hear me. Okay, so the first step is to first add this virtual 0 to the rightmost of 3. I'll choose 3 to be like the A for our case. Okay, so another tip is you need to know which number is better suited for A or B. So basically, the rule of thumb is if that number has a lot of subsequent like zeros and ones, you want that number to be A so that you can have like more of these do nothing parts. Okay, so anyways, so I'll choose 3 to be A. So then I'll add 0 to the rightmost of 3. So it becomes 0, 0, 1, 1, 0. And then you do the repeating steps, right? So first you check the 2 leftmost bit of the multiplicand, which is 3. So this one, 1, 0. Since it's 1, 0, then you want to subtract 5 from P, which is our result. So you first set your results to 0, 0, 0, 0, 0, 0. The rule of thumb is if you're multiplying 2 4-bit numbers, you need to have at least 8-bit for the result. So I'll let you guys think about why this is so by yourself. That's like it should be rightmost, rightmost, rightmost. Oh, yeah. It should be rightmost. I'm sorry. That's a typo. Yep, this one should be at rightmost. Right. Yep, rightmost. Yeah. Okay, then you subtract 5 from P. So you add the -5 to P. So it becomes 1, 0, 1, 1, 0, 0, 0. And then you arithmetic right shift both the multiplier and P. So both this one and this one, your arithmetic right shift, it becomes these two, right? These are our new M and P. So then we go to the next slide. Yep, so apparently I made the same typo for every slide. Right. So then you repeat the same step again. Thank you. Yep. Then you repeat the step once again. Just repeat number 2. Then you check that it's 1, 1. So this is the same. So you don't need to do anything. But then you'll still need to do the arithmetic right shift to both M and P. So you shift them shift them to right by 1 again. So this is now your new values for M and P. So on to the next step. And then, once again, this is the right one, the rightmost, right. And then now it's the third time we do this. We check the 2 rightmost bits. It's 0, 1, so this time you need to add. So now we need to add 5 to P. Then you can do like the simple binary additions to the most significant bit. And then you do the arithmetic right shift again for both M and P. So now our new value for M and P is this one. And finally, for our last repeat, right? I'm sorry for the typo. And finally, for the last repeat, we check the 2 rightmost bit, which is the same, so we don't need to do anything. But then we need to do one last arithmetic right shift. And finally, we have this. So this P is our final result. And I always urge you to recheck your result, like convert this back to base 10 and see if the result is correct. So this one is converted as 15, which is equals to 3 times 5. Yeah. So keep in mind on like the number of repeats. You want to repeat like four times in case if you're multiplying like a 4-bit number. If it's like 5-bit number, then you need to repeat 5 times, etc. So hopefully this is clear. I recommend you to practice this algorithm again with like a different number, maybe like multiplication of 2 negative numbers, 1 negative, 1 positive, just to make sure you get everything correct. Right. So that's all for boot algorithm. Right. So next, we'll start to go into the ALU, the arithmetic logic unit. So the ALU takes in three signals, or yeah, 3 signals. So the S is the 3 select bits. It basically tells the ALU which operations to perform. The CN is the carry in bit that we already discussed before. A and B are like the 2 N with input, which are like the numbers that we want to process. And then VC and Z are like 4 signals that the ALU output other than the result. So the V shows us if there's a result overflow. This is when we're like doing operations on 2 signed numbers, and then it ends up being bigger than the n width that we define. So if it's one, it means that the result overflows, and that means like the result is not, I guess, accurate. C is the carryout bit. N, if one, means that the result is negative, and Z, if one, means the result is 0. So it's quite simple. So next we'll see like this is the data path and control unit. Data path consists of the storage and the ALU parts. So storage is circled in red, while the ALU is circled in purple. While the control unit gives off like the signal to control all these parts to do basically what we want, right? So looking at the storage, we have 4 storages in like this simplified version of the data path. So you have the program counter, the main memory, the instruction registers that stores like all our instructions, and these are the register files that stores our temporary data. Okay, so register files are how the computer stores temporary data. So these are used to store data that you need to use quickly. So when you're doing the assembly program to make your games, you will notice there are registers names like $T0 or something like that. So these are used to store like temporary files that needs quick access. So register files consist of a set of registers, and you can refer to like one of these unit registers using a destination address, and the bit width of that address has to be the log 2 of the number of registers here. So if there are 4 registers, then you need an address that is 2-bit wide. So I hope that makes sense, right? So this one, the address is 0001, 10, and 11, so on and so forth. All right. So let's have like a short practice for register file. So assume we want to make a register file, like the picture just now, that can hold a total of 1000 bytes of data. And then we want to use a 32 wide register. We want to use 32 wide registers to build this. What will be the length of our address? So we want to store a total of 1000 bytes in our register file. and each of this register unit stores how is it? 32 bit. So how many register units do we need? And then how wide do we need the destination address to be? So I'll give you guys I guess 3 minutes to solve this, or maybe 2 minutes. It's quite simple. Feel free to put your answers in chat. All right, I see some answers. Hopefully it's long enough. Okay, so here it is. So first, we want the register file to hold a total of 1000 bytes. So 1000 bytes is equals to 8000 bits because 1 byte is 8 bits. And then we want to divide this 8000 bits by 32 because that's how much each unit of our register can hold, right? So in the end, we need 250 registers. So to make an address that can address 250 registers, we need the log2 of 250 wide address. This gives you around 7.9, and you always need to take the ceiling, right? Because if you take like the floor, which is 7, then it won't be enough to address all the 250 registers. So our address needs to be 8-bit long. It's simple, right? Right. So next one. So similar to the register file, we have our main memory. So this one can store a larger amount of data. However, it is slower. It is slower for us to access or store, read, or write into this main memory. So again, it's similar like the register file. The address lines needs to be the log2 of the number of rows bits wide. And again, you take the ceiling, and then each row can store like a specified number of bytes. So this one is different on every computer and every architecture. So this one is based on the questions. Right. So now we'll go to instructions. As we know, there are 3 types of instructions. There's the R type, the I type, and the J type. And let's go through each of them quickly. So the R type is structured like this. So we have the 6-bit of opcode, 5-bit of the source register 1, 5-bit of source register 2, RT, 5-bit of the destination register, RD, 5-bit of the shift amount, and 6-bit of the function. So in R type, the opcode is always 0000000. So if you are given an instruction and you need to, I guess, determine which type of instruction it is, you see the opcode, it's 00000, you immediately know it's R type. Okay. The shift amount, the Shamsi, is for bitwise shifting, like shift left logic or shift right logic. And this function, 6-bit, is to determine which operation to execute. Now moving on to I type. So the I type has 6 bits of opcode, 5-bit of source register, 5-bit of target register, and then 16 bits of immediate. So immediate is 16-bit value that can be used for arithmetic operations or memory offset. So for example, if we want to add, say, like a small number to like one of our register, like 5 or 8, we can just put it in the immediate in an I type instructions rather than having to like store them in a register first, then use an R type to do the addition, right? We can also do memory offset or branching. So I types are used for these types of operations. So for branching and memory offset, the question is, how can we store an address with only 16-bit? The answer is, it's actually we don't. So it actually stores the sign difference between, I think in this case, RS. Yeah, the sign difference between RS and like your target address, and it omits the to rightmost bit. So these are just like examples of like the different instructions. So you can see for branchings, those are all I types. Then there's like an R type addition, but there's also an I type addition, which is adding your immediate to like the register data. All right. Then let's do some practice. So assume we want to branch to a target address using an I type instruction. So the target address is this one in hexadecimal, and our current address is this one in hexadecimal. What will be the 16-bit intermediate be? So I'll give you guys maybe 3 minutes to solve this. You guys are familiar with hexadecimal like addition and subtraction, right? All right, let's solve it together. Okay. So first of all, we need to find the sign difference, right? Because here you go. So this one, you need to find the sign difference between your target and your current address. So first, you want to subtract 43 ABC4 with 44, 3, 5, 6, 7, 8. So I'm sorry for this one. It's a bit of a large number. It should have been shorter for your convenience. But if you do the calculation, it becomes 554C, and then you convert this to binary, which is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0. Now you can always remove the last two bits. These last two bits will always be 0. And why? It's because the instruction address are always in multiples of 4, right? So we can remove the last two bit, and then we'll do a sign extension until our immediate is 16-bit. So in this case, the final result is 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. Is it clear? Is this part clear? Honestly, it's just this part that's probably like a hassle to calculate. But honestly, I think in exams, the number will be much smaller and easier to calculate. So, okay. Yeah. How come the subject I got 5546 instead? Oh, interesting. Pretty sure it's 554C. 5446 instead. Okay. No, it should the rightmost bit should be C, right? Because it's 4 minus 8, but then 4 is less than 8, so you borrow 1 from C, I guess. But since it's base 16, you add 16 to 4 instead of 10. So it's 20 minus 8, which is 12, which is C. Yeah. Yeah, okay. Next type is the J type, or the, I guess, jump type, right? So you might wonder, what is the difference between jump and branch? So branch has the I type, jump is J type. So branch is offset. So you do the current PC or the current address plus an immediate. However, jump stores goes directly to the address. It stores the address, it stores the full address kind of thing. However, we only have 26-bit of address. So how do we store full address in 26 bits? So the trick lies in, first we omit the first 2 bits again, because it's always a multiple of 4. And then lastly, we assume that the 4 leftmost bits is from the current PC top 4 bits. Okay, so you assume that it's kind of like close in terms of like the address. So let's have like a short practice again. So you have this J instruction, and your current PC address is 453 to ABC. What is the full address that you will jump to? Okay. So I'll give you guys maybe 2 minutes to solve this, or to start solving it. You guys don't have to finish by the time I start discussing. Oops. Oh, sorry. Um, quick correction. I'm so sorry. So there should be another 0 here. So this is the opcode. My bad, my bad. If you're running on a 32-bit machine, shouldn't the PC has an address length of 8 bits? Since each bit is in hexadecimal, which will be translated to 4 bits in binary. Hmm? Sorry, I'm not quite sure about this question. Uh, Sorry, are you asking why the PC are always in like multiples of 4? Like why we ignore the rightmost 2 bits? Yeah, that was just my mistake because it should be 8. But I assume like there's another something here, 1. But anyways, you only need like this part for the question. It should be 8 bits. It should be like 8 numbers here. You're right. Okay, let's discuss it then. Eh, yeah. Okay. So in this type of questions, so first, since this is a J instruction, we need to just remove the opcode because we don't need it. And so this one will be the 26-bit of address. So we want So this is our current PC address, and then we want to find what is the full address that we will jump to, right? So first of all, we will add 2 zeros to the right of this 26-bit address to make this. And then you want to add the 4 highest bit of the current PC. So in this case, it's this one. It's 4. Since this is hexadecimal, this 4 will be translated to 4 bits of binary, which is 0, 0, 1, 0, 0. And then you put it on like the leftmost side of our address. So in the end, you will get this 32-bit address that we will jump to. And then finally, we'll convert this to hexadecimal. So this one becomes 4, this one becomes B, this one becomes C, 840EC. This is just a simple binary to hexadecimal conversion. And then we get our final target address, which is 4BC, 840EC. Okay, hopefully this is clear. Yeah, sorry for the mistake just now. This one is supposed to be 8 numbers long. All right. Yep, we discussed this already. So once again, recap, these are the 3 types of instructions. And okay, finally, we go to the data path flow. So this is the data path diagram that is shown to you in lectures. I really encourage you to be familiar with every part and like every wires, like where they are connected and everything. Because most probably there will be at least 1 or 2 questions regarding this. It came out like in my year, I think it came out in the other instructors' years too. Okay, so first of all, let's familiarize ourselves with like the signals that the control unit gives out to control this whole data path, right? So first we have PC write. It writes the ALU output to the PC. PC write condition only writes to the PC when ALU 0 condition is met. I or D, this one controls this multiplexers over here, which is a signal to select whether the memory address comes from the PC or from the ALU output. So this one connects to the ALU output. Let's crop. There's also the memory to register, which is this multiplexer, which is to select if the register file is receiving data from memory to ALU. So if you see over here, so it's either it receives the data from the memory or it receives the data from the ALU here. And then we have the IR writes, which is instruction register write. It's to tell if the instruction register is being written with a new instruction. And then next we have the PC source. PC source controls this multiplexer. It's to control whether the PC is from a jump or from the ALU operation. ALU op is to determine which ALU operation to perform, like addition, subtractions, etc. Give me an example for when I write is high. Okay, so Bobby or Valdy, can you answer this? Because to be honest, I'm quite confused too. I somehow, like in the slides example, we assume that the instructions were already written beforehand, so I write is always set to 0 for the example in the slides, but I'm not quite sure when I write is usually high. Be nice if
I'm I'm pretty sure like IR write is you only make IR write to high when you are fetching the next instruction. Le- Um
so in So for example, like if we have a question like say determine like the control signals for this
Yeah, so
instruction, we already assume that the instruction is loaded, right?
yeah, because like the fetching part of the instruction is like it's the same for any instruction, right? It's
Right.
just adding 4 to the PC.
Okay. So
Yeah.
for these types of questions, are there instances where IR write is high?
I guess for jumps, I guess.
For jumps.
And branches, but I don't think there's anything else.
All right. Thank you.
Yeah.
Yeah, that one confuses me too. Okay, so ALU op basically tells the ALU which operation to perform, addition, subtractions, or multiplication, etc. And then we have the register destination is which part of the instruction contains the address for the register to write to. So it's like whether it's RT or RD. I think you can't see it over here, but it's here. So which one to write? Like, is it from this section or from this section? All right, so control unit practice. Indicate the control unit signal values for each operation or for this one operation. If control signal does not affect operation, you can write X on it. So this one is a bit long, maybe 4 minutes, 3 minutes. So I'll give you time to write down these. Okay, I'll give you time to write down the operation, the SW operation, and then I'll move my screen to the data path diagram. Okay, so this one. So for this type of question, I recommend like going over the whole operation step by step. So start from like instructions, then you go to the other parts of the Oh, I am muted. I'm sorry. Yeah. No, I'm sorry. Thank you. Yes, in the exams, we're usually going to get the reference sheet for the instructions. So okay, so this is the answer. So the operation here is store word. So you want to store the data that is stored in register T0 and store it in the register of address T2, but you offset 8 from it, right? So just from the top of this, we can say that this is an I-type instruction because we have like this immediate that we need to store. All right, so let's go to the diagram and see which part does what. So first of all, we start from the instruction. So it's where we get our I-type instructions. And then in our I-type instructions, there is the RS and RT, which is the two register address and the immediate, right? So the RS address will be passed from the instruction register to the register file, as denoted by the red arrow. And then it'll be read, and then it will be passed to A here. Meanwhile, our immediate, which is 8, will be passed from this section of the instruction register down here. Then you sign extend so that it's the same length as the other operands and goes to this multiplexer, right? So in that operation, what we want to do is to add 8 to the T2 register over here, which is why we'll add these two numbers, A and B, then we'll get the result. So the result will be the memory address where we will store that new value. And then we will also need to find the address of the RT register. Yeah, ask what's the difference between ALU result and out. So ALU out kind of like stores the value of ALU result. So I think that's how it goes. Okay. Where was I again? Okay. This one, the RT register. Then you'll also need to read this RT register's the value inside the RT register. Remember, this is the value that we want to move to like that new address in memory, which is why we don't need it to go through the ALU. We just pass it straight down this wire to the memory. Okay. So now we have our new memory address that we get from adding 8, the immediate, to the address stored in RS. So it's denoted by the green arrow. All right, so we have the address of the memory and the value that we want to store in the memory. Finally, we can finish the operation by storing the value of T0 in that new address. Okay, so this is how things go in the diagram. From there, it's quite simple on what to decide the signals will be, right? So first of all, we have the let's go one by one. Oops. Okay, so PC write condition and PC write, we both set it to 0 because we don't do anything to PC. We don't write anything to it. For I or D, instruction or data, we see that we want to take the address that is outputted from the ALU, which is this green arrow here. So we want it to be 1, right? And then memory read, we set it to 0 because we don't read from memory, we write to it. And hence memory write, we set it to 1. And then next, memory to register. It's this multiplexer over here. As you can see, we never use this. So you can put an X there because we don't care. We never use this multiplexers anyway. For IR write, again, like your previous examples in the slides, we assume that the instructions are already fetched. So IR write is set to 0 right now. And then PC source, which controls this multiplexer over here. Again, we don't use it. So whenever we don't use a multiplexer, we can set it to X. Don't care. And then the ALU op, ALU op will be like whatever signals which tells the ALU to do the addition operation, which is doing this +8, this +8 offset. I'm not quite sure what it is, but you will be given a table for that. And then the ALU source B, which is this multiplexer, you want it to be set to 2, or if it's binary, then it's 1, 0. Then the ALU source A, which is this multiplexer, it's set to 1. And then the register write, which is this one, we set it to 0 because we don't write anything to the register. We only read the data. And then finally, the register destination, which is over here. Once again, we don't use this multiplexer, so it's set to X. So that's it. Is there any questions regarding the control signal and this diagram? Yeah, okay. Hopefully not. I recommend doing like more practices on like different operations. Try, I guess, load word or other things, and be comfortable with this diagram. So I'll give the stage to Bobby now to talk about the assembly part of the course. Thank you.
Yeah, okay. Can you guys hear me clearly? Yeah. Yeah. Okay. Then let's start with the assembly part of the course. So first, as you guys probably are already familiar, assembly is the lowest language you can go without actually writing machine code. And in this course, we're learning the assembly that's used by the MIPS platform, which is an RISC architecture with a simplified instruction set. And when dealing with assembly, at least in this course, you're mainly dealing with these key registers. So you have the temporaries, which are T0 to T9, safe registers, which are S0 until S7, registers for our function arguments, which is the A's, the return values, which is the V's, and then the stack and frame pointer. So yeah, let's jump right into it. So Frans already touched into this a little bit, but I'm gonna go over it again just for a quick review. So there are 3 types of instructions in MIPS: R type, I type, and J types. These are general guidelines, so R types are generally have 2 source registers and 1 destination. I types generally have 1 source, 1 destination, and 1 immediate value, while J types are jumps that don't have any additional arguments. There are some exceptions to this rule. For example, JR jump register is an R type despite being a jump. Same with JAL R. The branches are all immediate, despite some of them only needing one register. And all the shifts are R types. Here are some examples. So an example of an R type instruction is add. Here add T2, T0, T1 means storing the value of T0 plus T1 into T2. Add I is an I type. And in this example, we're adding 3 into T0 and storing the result into T1. And here, JAL is a J type. Here, JAL function name will be us jumping to the label function name, while storing the current address to RA. Right. So onto the general structure of an assembly code. So you will have two main sections, .data and .text. .data marks the start of the data section, and this is the section where you will declare and store global variables like arrays or other large data types. The text is where you write your code, your executable code. So an assembler will start running the code starting where .text is. And another common line of code that you have in assembly is .global main. This is to mark an entry point for the program when you are working with multiple files and you're working with linkers. In this course, you are not going much deeper into this. You're basically just told to write .global main every time. But yeah, you don't need to worry about that very much in this course. So let's move on. So in the data section, as I said before, you can store global variables. Here are the different types of keywords that you need to know. So first we have a dot word. Dot word is a word which is 4 bytes of data. Dot half is a half, which is 2 bytes of data. Dot byte is just 1 byte. And you can assign them to labels as in the slides. You can also create arrays. So arrays are just contiguous areas of memory where you assign consecutive data. So in this example, R will be the array 0, 1, 2, 3. And you can also create strings. You can create raw strings without a null terminator. So this will only contain HELLO, which is 5 bytes, with the .ASCII keyword. And you can also store C-style strings, which are null terminated. So you can do that with the .ASCII Z keyword. So this will be 6 bytes instead of 5 because you have an extra null terminator at the end. And then the next two you probably haven't used as much, but you have dot space and dot align. Dot space is to reserve an initialized space in memory. So you can reserve space for a 42 byte variable data structure, and then you can fill them out in your code afterwards. And then lastly, you have dot line. Sorry, is a byte enough to store 42? Yeah, I'm pretty sure, yes. A byte is 8 bits, so you can store up to 255. Yep, okay. So moving on, lastly we have a dot align. Dot align, I think you have seen this in the reviews. So dot align is to force alignment of bytes. So for example, if let's make this black for to make this more readable. Yeah, so if you have 4 bytes, if you have 4 bytes that you're storing consecutively, the assembler will not automatically store this in a word align area because bytes don't need to be word aligned. But if you want to force that, maybe you want to do some optimizations, you can do dot align 2 before you declare the bytes. So this will align the next data to the power of 2 bytes, which is 4 bytes. Right? So moving on, we're gonna jump into the code primitives that you see in you will see in a higher level programming language. We'll start with control flow. So, here the example that I gave is if A equals B, then we increment B by 1, else we decrement A by 1. So the way that you will do this in assembly is with branches and jumps. So here the first instruction is BEQ T0 T1 if. So if T0 is equal to T1, we'll jump to the if label here. And this if label will contain the if code that we have here. And the else code will be here. So if A is not equal to B, it will continue on to the next instruction. And this, as I said before, this is the else code. And after executing the else code, we go to JN, where we'll skip through this red line of code and jump straight to the end label. And next you have while loops. Again, you will do while loops with branches and jumps in assembly. So here we enter the loop, and then if here we're storing I and T0. If T0 is equal to 0, we will jump out of the loop. So N here is the end of the loop. And then after that, you will have some code here for the loop body. And at the end of the loop body, you have J loop. So you jump back to the loop, to the start of the loop, and check for the condition again, and so on and so forth. Next, we have for loops. So for loops aren't that much different than while loops. The only difference as you have stuff that you need to do before the for loop that's indicated here in the first part of the for loop, and the last part. The last part is it will be executed at the end. So here in our example, we will initialize t0 to 0 first and initialize t1 to 100 for the comparison. And if the middle part of the for loop is not satisfied, we'll break out of the loop. So we'll branch to n if t0 is greater or equal to t1. So t1 is 100 here, and t0 is just I. So if I is still less than 100, we'll continue on to the next line, which is just the loop body. After executing the loop body once, we'll increment I by 1, and then jump back to the start of the loop. Right. So on to the next one, we have functions. For function calls, you have faced 3 major conventions in this course. The first one is register-based convention, where you store your return values in the registers V0 and V1, and then you store the arguments in the registers A0 until A3. This is a very simple convention, especially compared to the ones that you stack that we will see later on. But it has its limitations because we only have 4 A registers, 4 arguments, so we're limited to 4 arguments and 2 return values. But it's still useful for simple functions. So next we have stack-based convention with callee, pop. So this is probably the convention that you are most familiar with, the one that you have used most. So this convention is more flexible than the register-based convention because you can push as many arguments to the stack as you want. So when we're following this convention, the caller first must push the arguments to the stack, and then call the function with jolf func name. And then once we're into the function, the callee or the function will pop the arguments one by one and then save them into the registers. And then the callee will push RA into the stack, and after that it executes the function body. Once the function body is done, the callee pops RA, pushes the return values to the stack, and returns with JR to RA. However, this convention also has its limitations, because since we're popping all the arguments at once at the start of the function, we are limited by the number of temporary registers. And if we have more arguments, then we will need to keep pushing and popping to the stack to preserve all the local variables, the arguments. Yeah. So, and the last convention that you have seen is the color pop stack-based convention. So this convention uses the frame pointer. So first, as the previous convention, the caller pushes the arguments to stack and calls function with shell func name. May I ask what's the difference between S and T? Do you mean the registers? Okay. Um. So both S and T registers are so T registers are temporary and S is safe registers. So um if the convention is usually for the caller of a function to store anything that it wants to save that are stored in the T registers. So caller saves T registers and the callee saves the S registers. Yeah, exactly. So the only difference is by convention, and they are the same functionally. They're exactly the same. Is that clear? Right. So after the caller pushes the arguments and calls the function, the callee will then push RA and FP, which is the frame pointer to the stack. So this is to save the old RA and FP. And then we set FP to the current SP. So FP now will point to the top of the stack, to the top of the stack, and then it will proceed by executing the function body. And in this convention, the callee or the function can make large local variables and store them into the stack. And then it can refer to the local variables by the offsets that they have with FP, since FP stays constant. And then the callee will restore SP with SP by assigning it to FP. And then it will pop the old values of FP and RA, restoring them. And then the function will push the return values to the stack, and as usual, it returns with JRRA. And notice that in this convention, the callee or the function doesn't actually pop the arguments off the stack. And that task is delegated to the caller of the function. So after the caller calls the function, the caller will have to pop both the return values and the arguments. Should callee retrieve the arguments from the stack first before it pushes RA and FP? No. So after you push RA and FP to the stack, you can still access the arguments by using negative offsets to FP, right? So yeah, okay. I guess that's clear enough. Yeah, so the appeal of this convention is that everything stays the same offset relative to FP, since FP is not changing during the lifetime of the function. And yeah, and this is just as a fun fact, most programming languages implement a hybrid of these three conventions. Usually they will store, if the function requires very few arguments, they will first use the registers first usually, but it differs between implementations. Okay, so next we have recursion. As in any programming languages that you have seen, with recursion you have two main parts, the base case and the recursive steps. And the important thing to remember when writing recursive code is to save RA and parameters or any value that you want to store. that you want to preserve before the recursive call, because the recursive call can override them easily. So here's an example, a classic example of a factorial function. So first, we pop uh the first arguments into T0. I think there should be, you should restore the stack here. After popping the arguments. Sorry that I missed that. And then we will branch to the recursive case if T0 is not equal to 0. And in the recursive case, you will save T0, get n minus 1 for the factorial, and then call the recursive function again. And if instead T0 is equal to 0, it will go on to the base case here, and it will return 1. Okay. So here I have some practice questions, a 3-part practice question for you guys. So our task is to write an assembly function called min-max that takes an address of a non-empty integer or word array and the length of the array, and returns both the maximum and minimum element of the array. So first we will need to do it using a loop. And then using recursion. And the third question will is to write a global assembly code that basically calls the two functions and compare the results. I'll give you guys 5 minutes to try these exercises out. And yeah, we'll see you in 5 minutes. Okay, so it's 4:36 already. Let's start the discussion. So for these assembly coding questions, if you are more comfortable with assembly, you can go ahead and directly write an assembly. But otherwise, I would recommend to start with a pseudocode or just code in the language that you're most comfortable in. So yeah, let's start with that for the first question first. So we want a function that accepts two arguments, an array, and the length. And we'll first need to assign two variables for holding the temporary min and max. And then you will need an index. So the next index will be 1. And basically you'll do while I is listed length. If the entry at that index is listed min, then min, we assign min to that value. And if it's larger than max, we assign max to that value. So now our task is to convert this to assembly. When converting to assembly, I usually like to minimize the number of variables that I'm using. So in this case, we can make a few optimizations. First, we can change. Oops, I forget to increment I here. First, instead of incrementing I, we can increment the array since we don't need the previous elements. We are only considering the current and the next elements. So you can modify this without I. And then instead of incrementing I, we can instead decrement length until the length is until the length is equal to or less than 0. You don't need to do this, but seeing like these little optimizations can be important for questions where they ask for them. So yeah, let's jump into the assembly. So if the question doesn't specify which conventions to use, you can use whatever you're most comfortable with. Here, since we only have 2 arguments, I'm using the register-based convention. So I'm assuming that A0 stores the array and A1 stores the length, and we'll return min at V0 and max at V1. So as always, first you need to pop um you need to uh sorry, we're not popping because this is a register-based calling convention. So here I'm assigning v0, which stores the min, and v1, which stores the max, to their initialized values, which is the first element in the array. So first we're loading from A0, which stores the array, and we're getting the first element with the offset 0. And then we're copying that value to v1. And then here we're decrementing the length that is stored in A1. And if the length is less than or equal to 0, we'll jump to the end of the loop. So we're going to the start of the loop here. Here we increment the address of the array, and then we'll store the the new first element of the array into T0, and compare the value in T0 to V0 and V1. If it's greater than the min, we don't do anything to the min, so we jump to min done here. If it is less than min, we will move T0 into V0, and we'll also do a similar thing for the max. And when we're done, we decrement the length by 1 again. And then if the length is still greater than 0, we'll jump back to the start of the loop to start the process all over again. And when we're done, since v0 and v1 already stores the return values that we want, we can just return. I guess I made a couple of errors here. Yep, so any questions? If not, we can move on to the recursive version. So again, we'll write a pseudocode first. Of what we want to do. So if length is equal to 1, we just return the first element of the array as both min and max. Otherwise, so this is the base case here, and otherwise we'll jump to the recursive case. So I guess here we need a temporary value for min and max. And then we update them accordingly. Then we do the recursive call. Which is doing the function call with the incremented array, the decremented length, and the new mins and max. So let's go to the assembly version. So here, the first line, we decrement the length here. And then if the remaining length is greater than 0, we'll go to the recursive case. If not, we'll go to the base case here, where we'll just return the value of the first element in the array, which is stored in A0 and offset 0. So no, and notice here that we can also use recursion with the register based convention, although you usually won't do this. But in some cases this can be simpler. So and then in the recursive case, you push RA to the stack before the recursive call. And then you load the the frontmost elements of the array to T0 and then store that into the stack. Increment A0 by 4, so this points to the next element and call the function again. This is the recursive call. And then we can restore the value for T0. This is the value of our value of X. And then do the assignments for min and max. Recover the value of RA and do the function return. Right. So the next question is to write an assembly code that compares the two return values of max min and rec max min. I'll just go right into the assembly here. So first, here we declare the array, success and failure variables. So the array will be a word array of size 10. Success and failure are just C strings. And then we'll jump right into the code. So we'll input the arguments in A0 and A1. So A0 will be the array and A1 will be the length. Call min max. And then store the results in S0 and S1. After that, we reinitialize A0 and A1 again. So A0 is the array and A1 is the length. And then we call the recursive min max. And now V0 and V1 will store the max and min from the recursive function, and S0 and S1 will store the return values from the non-recursive functions. And then now if either one of them are different, we jump to the fail case. So we'll go over the fail case first. In the fail case, we print, this is a typo here, it should print failure. because we're loading failure into the argument. And then we do LIV010, which exits the program. Syscall access program LIV010 provides the trap code to exit. And similarly, in the success branch, we print success with a syscall and exits the program with trap code 10. Yeah, and that's it. If you have any questions, feel free to ask in the chat or open up your mic if you want. We still have 10 more minutes. We'll probably stick around in the Zoom in case anyone have any questions. But yeah, thank you.